Okay. All right. Let's see who remembers the old tangent of y. Oh, very clever kids. I'm impressed. Derivative of tangent is secant squared. The base stays the same. Chain rule is y prime. Okay. And derivative of x is 1. Okay, this is a good reminder on all those derivative rules, actually. Okay, so what I have 3 different y primes, but I want to isolate them. Okay, isolate them. Yeah, well, we factor to the front. Okay, factor. Tell you what, eventually you'll have to do this. Isn't natural log of 3 just a number? If you did natural log 3 on a calculator, hit enter, you get a decimal. So if it's a number, isn't it a coefficient? So eventually, again, I wouldn't count off of that, that's pretty picky, but it'd be nice if you would move it to it as a coefficient to the front. Okay? So that's a good move. And then that's going to be secant squared of y. Okay. All right, almost there. All we have to do is divide everything by all this business. Okay, so all this goes down to the bottom. Just like in middle school when they said to solve an equation, keep doing the opposite to both sides. That's all we're doing. Okay? On a bigger scale, but keep doing the opposite. Ah, nuts.
Fraction, actually.
I got a fraction in my fraction.
Y over y.
Okay? Good idea. What I want to what I want to eliminate, move, okay? I want to lose the y because the y is a fraction in a fraction. So to get rid of the y, I can introduce another y to the problem. Y, problem y. Introduce. Okay. And then you can distribute that, but wait, you can't just send a y through there. Thanks for changing my problem. All right? If you do one on the top, it's okay. Okay? Because y over y is a big 1, and that's okay. All right? So if you ever see that fraction in a fraction, don't do the common denominator way. It's just too hard. Just send that y through there. It takes care of everything. So what do we got on the top then?
Y.
Y. All right. What's y times 1 over what? 1. As planned. Got rid of the fraction. What is y times this? Well, it's just going to be y and all that stuff. All right. Okay. Let's write it as natural log of 3. Probably want to put the y second. If you want the professional formula. Probably want to put the coefficient first. Okay. Y, and then that's 3 to the y, not cubed. Okay? And then what is y times secant squared of y?
Y secant squared of y.
Y secant squared of y, sure. Okay? And that's the perfect answer right there, and that will give you the slope of all this crazy business. You can imagine at those corners, you're going to get an undefined slope when you try it out over there. Okay? Interesting stuff. All right. Now we get to the last section there, which is xy equals e to the y. And you can see the graph. The graph is kind of like a floating half of a hyperbola, and then another little curve over there by itself. Interesting. And there are all these combinations of xy's that don't work. So that just maps out the ones that do work. Well, 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 what do we have here? Okay, differentiate. Fancy word for take the derivative of this. But you know what? X and y are both called variables. And if they're both variables, the only way to do this derivative is to do the product rule. Because it is the multiplication of variables, right? Now, what did we do in the past? In the past, we had like x times sine of x, let's say. I hate these. Okay? If you had x times sine of x, isn't that a variable times a variable?
Yes, it is.
Now we got an x times a y, but it's still a variable times a variable. All right, so the product rule would be, how does it start off?
OD high.
Okay, OD high. So it would be second stays the same times d high, 1, plus high d ho, x times the derivative of the second term is, oh, okay, there you go. That further illustrates our main theme of the day, which is the derivative of x is going to be 1, but the derivative of y is y prime. And what about e to the y? Remember this one? Stays the same. Natural log of the base, which is 1. Y prime. Okay? All right, now, we've got to get y prime by itself. We have done the calculus. Pre-calculus, right? all we have to do is a little bit of algebra here. Can you get the y prime isolated? You know what's wrong right now?
They're on the same side.
The y prime buddies aren't together.
You have the lines and
Okay.
beams in the same place.
Could I take this and just subtract it over? Yeah, let's do that. Yeah, remember? Yeah, that's right. We did play this game this year. Forgot about it. It's our old game called Cheetahs and Kids. No, it wasn't Cheetahs and Kids. It was Cheetahs and something.
Crocodiles and chickens.
Yeah, something like that. Yeah. Okay. So I got cheetahs. I got not kids. Let's not use kids. Something else.
Oh, birdie.
Goats.
Yeah, goats. Okay, yeah, they like goats.
Gazelles.
Okay, gazelles. Yeah, okay, yeah. We got gazelles, cheetahs, and cheetahs. Whoops. Okay, let's put the cheetah over here. All right. So this is going to be e to the y prime minus x y prime. Scoot it over. Now we got them on the same side, but wait a minute. I've got two y primes that I want to isolate. Why don't we factor it out? That is a good idea. Okay, up, almost there. Take this, divide it down, and y prime will be defined as y over e to the y minus x. And notice again that your derivative has a mixture of x's and y's, often in these cases. Okay? All right? So that makes these derivatives a lot easier because you would not want to solve these functions for y. That would be terrible. All right? Now, the last thing is find the slope. Okay? So let's find the slope of this random curve here. It goes like this and this. Find the slope at e squared over 2 comma e, wherever that is. Seems like an awfully random point, doesn't it? E squared over 2 comma 2. Did I just make that up off the top of my head?
Yeah.
Or does it have to work in the formula?
That's working the formula.
You know what? If it doesn't work in that formula, then it's just a point floating in space. Remember that? I had to pick a point on the curve somewhere. So let's test it out. Let's see if I actually got it right. If e squared over 2 is the x coordinate, and the y coordinate is what? 2. Does that work?
Yeah.
I put in 2 for the y and e squared over 2 for the x. Oh, it works, doesn't it? Nice. Okay. If that doesn't work, then your point's floating in space. It's not on the curve. Okay. So I picked one that actually worked. All right. You can't just do e squared over 2 comma 17. It doesn't work. Okay. So at that point, what is the slope? Now the slope is the what? Derivative. Could I just take e squared over 2 and put it in for x? Oh, and then also put 2 in for y. What's the implicit difference? Usually you have to plug in x's and y's, not just the x to find slope. Okay. So that's possible. So it'd be 2 over e squared yeah, minus e squared over 2. Okay. So 2 over e squared minus e squared over 2. All you have to do is simplify that. Now, 2 ways you can do this. Disguise that as 2 over 2 and get it in the denominator. Easier way to do it though. Somebody gave me an e squared for my birthday. Somebody took away half of an e squared. I have a half of an e squared left. How about that? That's a shorter way to do it. Okay? I'm going to skip the common denominator. I got a whole e squared minus a half e squared is still a half e squared. And then you can reciprocate and make it look like this, and that is what? 4 over e squared. Therefore, the derivative at this point is a positive number. Hence, the only way that a derivative could ever be positive, or slope of the tangent line be positive, is if the graph is increasing, so you just verify increasing. Got to be on this piece up here. Okay? All righty. Catchphrase. Hey, Jordan.
Yeah.
You want to turn it off?
Just a sample test. All right. First half on